Hi again. Last video was cut short. We were solving question number 31. I have here the values filled in. We would get an answer of I'm just estimating something around 6. If I'm estimating A is about -10. So that would make our answer for question number 31, choice 2. And question 32 is another modern physics question, so we can skip that one. So moving on to the next page, starting with number 33. A circuits question: which circuit has the largest equivalent resistance? Well, we know that resistance adds differently, whether it's a series circuit like the first two, like choices 1 and 3, or parallel like choices 2 and 4. So if you don't remember how to add resistance in series and parallel, you have it right here on page 4 of your reference tables. Here's resistance in series, there's resistance in parallel. Looking at the circuits, I would just add them all up one by one. For series, I'm adding them together. 2 plus 2 plus 4, that's 8. 2 plus 2 plus 6 is 10. Okay, so we have an 8 and a 10. Going across the bottom, we're adding inversely. So that'd be 1/2 plus 1/2 plus 1/4, and then inverting that. So let's see, half plus a quarter. We're talking about 5 over 4 inverted, so that's 4 over 5. So that's definitely less than the first two. And then 1 over 2 plus 1 over 2 plus 1 over 6 inverted. That's going to be a small number as well. In fact, you guys may remember I mentioned that when you add resistance in parallel, each one you add decreases the total, such that the total is always less than the smallest resistor. So without even doing the equation, if you knew that, you could say, oh, well, look, choices 2 and 4, the equivalent resistance must be less than 2 ohms, because those are the smallest resistor in each case. So the largest equivalent resistance would be choice 3, the 226 combination in series. We can move on to question 34, wave question. Transverse wave moving to the right. We want to know which direction point X will be moving at the moment we are seeing the wave. Well, if the wave is moving to the right, point X is just a point of the medium, a point of the string, so to speak. And because the wave energy is moving along to the right, it's moving that point in the string in a certain direction, specifically in the upward direction based on where point X is. I can pull up the simulation of waves if this may help visualize what's going on. This would be the waves on a string simulation. We have used it, not necessarily with a particular lab. We use the real life Slinky, but this simulation could help, again, with the visualization. So let me just let a wave pulse happen. I'll put it in slow motion. So just focus on, say, this green dot in the middle. So the wave's going by, and the wave pulled it up as the wave was coming in with a positive amplitude. So wave coming with a positive amplitude, that point will go up as the wave passes through. Now this picture is a periodic wave, not a single pulse like I just showed you in the simulator. But again, the positive amplitude is coming into point X, therefore it will go up, choice 3. Number 35 is a magnetism question. We will skip that. Now, next page of the exam says part B. These questions are still multiple choice, but they might be a little bit tougher, maybe multi-step. Question 31, which measurement is closest to 1 times 10 to the -2 meter? Well, we just have to know what that means. That would be 1/100th of a meter, also known as 1 centimeter. 10 to the -2, of course, means centi. So that this question relies on your familiarity with what a centimeter looks like. It's like this. So how long is that? Oh, I don't know, maybe the width of a finger? Sure. About a centimeter. Choice 2. Number 37, which graph represents the relationship between a freely falling object and its speed? So speed, not velocity. So we don't really need to worry about negative signs here. Gravity's acceleration is a constant 9.81, meaning it will constantly change the velocity of an object, at least vertically, at a rate of 9.81 meters per second every second. that is a linear relationship between speed and time. Therefore, our speed will increase as we fall at a linear rate. Choice 4 is our answer. Number 38, a hair dryer operating as a piece of what will be a parallel circuit, assuming there are other things plugged into the outlet. We don't need to know it's a parallel circuit. We have information about the resistance, the voltage, and the time for this hair dryer in operation. And our question is for total electrical energy. So we just go to our equations. We look up the equations for electrical energy. So here's page 4, electricity. Work is energy. We have a lot of options. Based on the information we have, voltage squared times time over resistance is the combination of values we have available to us. So that would be 120 squared over 9.6 with a 2.5 for time. However, you can't use 2.5. That's measuring minutes. That's why this is a two-step problem. So let me write this all down. Power equals V squared times T over R. Our voltage was 120. The resistance, I believe, was 9.8. No, 9.6. And our time is 2.5 minutes. Well, 2.5 minutes, 60 minutes each second, that leaves us with 180 seconds. And here's the squared for the voltage. So we multiply and divide out all of these values. We'll wind up with an amount of joules of energy, and that would give us choice 4, 2.3 times 10 raised to the 5th. Number 39, a box weighing 46 newtons, that's its force of gravity, rests on an incline, angle of 25. What's the magnitude of the component perpendicular to the incline? Okay, so let's get a little picture of an incline here. 25 degrees with the horizontal, that's the incline. Now the box on top of it has a gravity force equivalent to, I've already forgotten, 46 newtons. Okay. And we are asked for the perpendicular component to the incline. So that would be this one. Well, there's also a parallel component, what I call gravity x, perpendicular component being gravity y. You need to know that your angle given with the incline is also adjacent to the vertical component or the perpendicular component. So our equation here would be for the perpendicular component. You see how the angle is adjacent? That means cosine is involved. We'll take the full force of gravity and multiply by the cosine of the angle. Plugging in 25 for the angle, 46 for the force, we will have our answer. And that is choice number 3, 42 newtons. Rounded, of course. Number 40, which graph represents the motion of an object traveling with a positive velocity and a negative acceleration? So positive velocity, negative acceleration means you're slowing down. That's like when you're braking in a car, moving forward, but accelerating backwards so that eventually you will come to rest. That means our position is still increasing. We're still moving forward, but the rate at which we're moving forward over time is diminishing because eventually you will be not moving, meaning your position will hold constant. The graph that represents this is choice 2. The position is going less and less and less as time goes by until eventually, if we could keep seeing the graph, it would flatten out, and that would be when you were at rest. So 40, again, choice 2 is what we're looking for. Number 41, we have cars A and B. They're both moving at constant speed. Car A 20 meters per second, car B 15 meters per second. They're initially 200 meters apart. And we want to know how far car A moves when it catches up to B. All right, so one thing at a time. We can, for the moment, ignore the fact that they are 200 meters apart and just consider how they're moving relative to each other. The difference between their constant velocities is 5 meters per second. Car A is moving 5 meters per second faster than car B. So their relative movement is as if car B is not moving and car A is moving at 5 meters per second, relatively. So if that's the case, we can now put that together with a 200-meter difference in initial position and say, all right, well, how much time does car A need to catch up to car B because it's going 5 meters per second relative to a stationary car B? Well, 5 meters per second going 200 meters, that means we need, according to this equation, or you can use this one if you prefer, same thing, 40 seconds of time in order to catch up, for car A to catch up with car B. So if car A is moving for 40 seconds before it catches up due to its relative 5 meters per second faster than car B's velocity, then we can now combine that 40 seconds with its actual velocity of 40 meters per second. Oops. Sorry. The distance it travels is its velocity of 20 meters per second multiplied by the 40 seconds of time. The car will travel 800 meters in the 20 seconds it takes to catch up to car B. So choice 3, I suppose. Question number 42. We have a resistance, we have an electric current, and a total charge. Total charge is the question. We have a 15 seconds for time. So the question is asking for charge. Once again, we have resistance, we have current, and we have time. Well, there is an equation that is the definition of current equation right here, which says current is a measurement of charge over time. So we don't need the resistance in this case. It's an extra piece of information that is unnecessary. 2.4 milliamps, 15 seconds of time. Okay. T and I. Now milliamps is no good. I'll replace the milli with 10 raised to the negative 3. And our equation, once again, is Q over T. Okay, so it's just a math problem now. This is your current, this is your time, solve for Q. Plugging it in, you will see an answer of 3.6 times 10 to the negative 2 coulombs, or that would be 0.036 coulombs. And number 43, we have a 1,000 kilogram car moving at 20 meters per second towards the east. It experiences an impulse of 2,000 newton seconds to the west. What's the final velocity of the car? Okay, so this is a multi-step problem. Impulse changes momentum, and it's equivalent to force multiplied by time, but we already have the impulse of 2,000. So let's figure out the initial momentum of the car. 1,000 times 20. All right, so that means it has an initial momentum of 20,000 kilogram meters per second towards the east. It experiences a 2,000 newton second impulse to the left or the west. So we have 20,000 units of momentum being changed by a factor of 20,000 the other direction. So it's a subtraction problem. The change of momentum and impulse can be subtracted from each other because they are the same thing. So we'll end up with a total momentum of 80,000 kilogram meters per second, still towards the east. But that's not the full problem. So I apologize for not writing equations as I'm writing this, but momentum is mv. We have our, 1,020, 20,000 units of momentum. Take away 2,000 because it's east, that's why it's negative. We have 18,000 units of momentum remaining. But that is equal to the new m times v of the object. So if the object is 1,000 kilograms of mass, its new velocity must be 18 meters per second. And I suppose that would be choice 1. That's the end of this page. I'll make one last video for the rest of the exam.